the main thing that I want to impress is we've all talked about this Bayesian framework, but how we actually calculate this likelihood physically, what we have to do in order to do this inference. And then I'll start to talk about some things that we might want to do differently and try to justify why we might want to, especially as we start moving into a sort of data-driven era where we have far more events that we're trying to deal with. And then, depending on time, there's a few more little fun things that we can do with our results to get nice visualization tools, really. Okay, I'll start with some definitions, which will be very much a non-exhaustive list, but since we pointed out that everyone uses slightly different notation for these things, I thought I'd just take a moment. In general, we talk about data a lot of the time. Just a reminder, this is calibrated in from to strain is what we generally take as data, labeled D. People, when they're doing these population analyses, sometimes forget that they're analyzing strain data, and they think that they're analyzing posteriors for events, and they forget that actually it's data. You've just hidden the data behind these posterior samples. And then we have each event has its own set of parameters which are unique to that system, the masses, the spins, or whatever, so these are theta. Then this lambda will be population level parameters, so these are anything that's common between many events. So it could be the maximum black hole mass, it could be the Hubble constant. Any of these are population level parameters. For computational ease, as you'll see, we use fiducial populations a lot, which is one of these things that allows us to hide the strain data from our analysis by having this fiducial analysis. So if you see lambda naught, this is just some fiducial population. People are free to assume whatever they want for that. And generally, if you see a fiducial population multiple times in the same equation, it's not necessarily the same fiducial population, which can cause issues sometimes. And then our standard Bayesian things, a likelihood is data given some other quantity. This I'll try to label L. And a prior that we assume going in, I'll give a label pi. But there are some things that some people might call priors that I'm going to try to avoid calling a prior for today. So we can see that kind of more specifically here, going from left to right, we have our posterior for single event and population parameters given the data. This is what we really want to know. These are the astrophysical parameters we're trying to infer from our data. And then standard Bayesian stuff, we have our likelihood of the data given the per event parameters. And you'll notice here that I've explicitly not included lambda in here. This is because we assume that each of the observations we make are different events, and so you don't really care about the population level when you're writing down the strain. What the strain should look like doesn't depend on the population level for individual events. We have some population model, which you'll sometimes see as a population prior, people will call it. That it's a conditional prior, conditioned on the population parameters. So I might use that interchangeably, talk about population priors or population models. It's really all the same thing. And there you have single event parameters on the left and population parameters on the right. And then I'll try to exclusively use the prior for population level parameters, because these are kind of the top of the hierarchy we have. When we talk about this hierarchical analysis, it's because we have some set of parameters, which are the theta, the per event parameters, and you can think of the population level parameters as existing on a sort of higher level. If you draw the diagram, that these population level parameters are on some different level in a hierarchy of parameters. And you can keep sort of adding more levels to your hierarchy to try to model everything in the universe. So we have many events, we want to combine them. And so we generally assume that all of the mergers we observe are independent draws from some global distribution of compact binary mergers, and the rate depends on the specific intrinsic parameters. You might hear people say inhomogeneous Poisson process. That basically means that the rate of 30 plus 30 binaries is different from the rate of 5 plus 5 binaries. That's what makes it inhomogeneous. The rate changes with the mass and the spin and those kind of things. And it's a Poisson process because we assume it is because it's a random process, and those all tend to be time of arrivals are Poisson. And the other thing we do is we assume that the strain data are uncorrelated between observations, which if the strain from the mergers is uncorrelated, then the noise is not typically correlated with itself over hours to years, so you can safely assume that all your data is uncorrelated when you're analyzing just short segments around each observation. And what that means is you get this thing where you multiply the likelihood for each of your individual events together, and then you add on some Poisson term that is this e to the minus r. And you can see there's a rate term inside here, inside this product. You can put it outside if you want, but it doesn't really make a huge difference. But basically, you have a rate to the power of n, e to the minus r, which is your Poisson thing. But unfortunately, we are subject to selection effects. Not all the mergers throughout the universe are observable. As Maya pointed out, there's this strong scaling with mass of the detectability. And so we tend to characterize this in this way, where this quantity alpha, I believe Maya called beta earlier today, is the fraction of all sources that are detectable, assuming some population model. So this depends on the choice of population model. And then above that, you can say what's the probability that I'll detect a binary with some specific set of parameters. Turns out to get that, we have to integrate over all data. Crucially, this is not just the data containing the observations. So you can't just look at 4 seconds around each observation to calculate your selection effect. You have to integrate over all of the data you have. And then our selection function we generally take as some step function where we define a detection statistic, and if it's above the threshold, we say it's real, and if it's below the threshold, we say it's not real. There are some ways to get around this, but this is the current paradigm. And then the total fractional observable events, you just integrate the observability for a given binary over your population model, and you get that. So great, that's a nice 15-dimensional integral for us to do. Also, is this integral over all data, which is an interesting thing to try to define. But anyway, once we plug all this in, basically the selection effect means that instead of observing all the binaries, we observe this fraction alpha of them. So the observed rate is going to be less than the true astrophysical rate by this factor alpha. And so when you put that in to your Poisson term, it turns out that basically all you need to do is to add this extra alpha up here to your rate parameter. I could go into more detail about why there isn't another alpha in here, but basically, depending on how you derive it, you can show that it cancels out, and this is the thing you get. So we have our posterior probability of data, posterior probability given data and astrophysical merger rate. Depends on some selection bias term, and then we product over all events. We have some per event term that depends on the data, the single event parameters of that event, and the population level parameters, and finally some population prior. So great, this is the posterior. We just want to know what this is, easy. So a quick aside before we move on to other things, I'm going to just run over some integration methods. Maybe you've heard about all of these things before. You've definitely heard about some of them before. Analytical integrals, this is basically where you know the answer, and you just write down the answer, and you put that into your code. Quadrature integration, we've all used, maybe not called it necessarily this, but basically if you divide your space up into a grid and then you sum over that grid in some way, that's a quadrature integral. We're all quite comfortable with that, but they scale quite poorly with dimensionality. If you try to make a grid in 60 dimensions, you find that your exponential scaling of number of grid points will break your computer. And so what we rely on instead a lot of the time are these Monte Carlo integrals, which I'll spend more time on. And then there are other methods that are kind of related to Monte Carlo integration, but just slightly smarter. That one example is nested sampling that you'll hear a lot more about tomorrow. Just as some example of an analytic integral that we can do that will prove relevant later. I don't really need to go through this in detail, but you have some function that you want to integrate, and then you ask Mathematica what the answer is, and then it tells you the answer. So here, we'll see that if you have something that looks like r to the n minus 1, e to the minus alpha r, the answer is alpha to the minus n, which we'll come back later. Again, won't dwell on this. This is just standard trapezoidal rule integration, where you have some points. But here, one of the things is you have to be able to evaluate your function numerically at all of the points of interest. And so that's going to be kind of a condition that can be hard sometimes, is having to actually be able to evaluate your function at all of the points. And so Monte Carlo integration basically depends on being able to write the integral you want to do as a product of two things. And then what you can do is you can draw samples from one of the terms in your product and just evaluate the other term at all of those samples in the point. And it turns out that this is an estimator of this total integral. So the sort of classic example that's probably the first Monte Carlo integral you'll hear about is estimating pi. So what this is doing here is this is estimating pi through randomly dropping points between -1 and 1 in 2 dimensions. And then when you take the magnitude of the distance from the origin, if that's less than 1, you count it, it's within this. And if it's outside, if it's blue, you give it 0. And it turns out that this converges on pi on 4. Yeah, pi on 4, because it's the ratio of the area of the circle bounded by the square. And so this gives you pi on 4, which is one method you can use to calculate pi. But there's something that you always have to keep in mind when you're using these numerical integrals rather than your analytic integrals is you always have some uncertainty that comes into this. And so this is something that we tend to ignore quite a lot. We're getting better about not ignoring it, so I've put it kind of front and center here. But here you have your integral that you're estimating, and that's fine. But instead of stopping there, you can quantify the variance in your integral. And that's basically the measure of uncertainty you have. You estimate this quantity, there's some error bar on it. Unfortunately, with Monte Carlo integrals, you can calculate that numerically as well. And I just added in here this extra term, which will be useful, which is the uncertainty and the log of the quantity, which is just the uncertainty divided by the thing. And the point that I wanted to make here is that this scales as approximately 1 on the square root of the number of points you have in your Monte Carlo integral. So if you're doing a Monte Carlo integration and you find that the uncertainty is plus or minus 2, but really you need it to be less than 1 to trust the result, you have to use 4 times as many points. And so it becomes 4 times more computationally expensive just to batten down this uncertainty. So when you're doing these Monte Carlo integrals, what you want to do is basically find the best possible way of dividing your function between f and g so that your uncertainties are minimized in this integral, because you don't want to have to add more points to make it converge, because it converges very slowly. So then we can move on to actually applying some of these integration methods, the way we do it. So this is the selection function that we had before. I've just written out as a single double integral, where we're integrating, as a reminder, over all of the binary parameters and also all of the data that we ever take. And so for double Monte Carlo integrals, what you can do is essentially sample from both of the distributions you're looking at and then just make pairs of samples. So you sample one set of masses and you take one little piece of data and you put them together, and you do that 1,000,000 times, and then you're doing an integral over this sort of producted space. And so what we do is we take all of those pairs, and for each of those pairs, we inject a simulated signal into this data bit we've chosen, and we ask, have we passed our threshold? And if we have passed our threshold, we add that to the accepted list, and if not, we put it in the rejected list. And so this is when people talk about doing injection campaigns to estimate sensitivity, this is what they're doing. They're drawing pairs of binary and data and then seeing if they pass the threshold. And there's one other thing I've added in here, which you'll see. We've drawn samples now from a fiducial model. We've introduced a fiducial set of parameters, which is that it's really expensive to do this. And so what we do is we do it once. We draw some fiducial set of binary parameters to pair it with our data, and then we want to change our population model later. Say we do these injections assuming a uniform distribution of masses from 5 to 100. But then we come along and say, that's a terrible description of the distribution of black holes we've seen. What if instead we make it look like a power law between 10 and 50? Well, then we have a new population model, which is this p of theta k given lambda is between 10 and 50, and p of theta k given lambda naught is between 5 and 100. And so what we do is we can rewrite this Monte Carlo integral we had before, where you take this p of theta given lambda, and you turn that into p of theta given lambda naught times p of theta given lambda divided by p of theta given lambda naught. Basically, you multiply by 1 in your integral to change what you draw the samples from to do the integration. Then the final note on this is, in practice, this is a step function. So when you're redoing this integral and calculating all these weights, there's no point in calculating weights for something that you're then going to multiply by 0. So you just keep what we call the found injections. So typically, we'll generate, for the LIGO searches, Reid can correct me, it's something like tens of millions of samples, and then we find that we only accept about 20,000 of them. And so this makes this much more efficient. I should have said this at the start, by the way. I'm going quite quickly through very technical things. Please interrupt me if something is not clear or you have any questions. And so yeah, this is the final thing. This is an integral that we have at the core of our analysis, is this sum over found injections of this, or this quotient here. So great, we can now evaluate our selection function numerically. So we can integrate some more things. We can bring back this analytical integral we saw before, where you have this rate to the n that we had on a couple of slides previously, e to the minus alpha r, which turns out to be essentially the same integral I wrote 3 slides ago. And then you can then apply some prior on the rate. One that we use a lot is you use a uniform in log prior. And the reason we do this is this just happens to give us a factor of alpha to the minus n, which is really convenient because then you wind up, you have n factors of, you have n events and you have n factors of the selection function. So they seem to match up really well. But you can use any other prior you want on rate. For example, the Jeffreys prior on a rate or a Poisson process. Jeffreys priors are these things that minimize information difference. Technical thing, not super important. But still, you can use this Jeffreys prior and still write down the likelihood marginalized over the rate, which is kind of handy because sampling for more parameters than you have to is going to make it slower and more difficult to do your analysis. And also, so speaking of reducing the size of the parameter space, we're carrying around these 15 binary parameters for every event, plus potentially parameters describing calibration of the detector and other things like that. So why don't we just integrate out all of these single event parameters while we're going, and then we find that we're just left with the probability of the population model parameters given the data associated with each event. And so this is great. We can just write nicely. This integral here is the likelihood of each little data that we observe given the population model. So if we can evaluate this, this is great. We've now simplified this likelihood hugely, right? We've got just this marginalized likelihood divided by the selection term multiplied by prior. So how are we going to do this? This looks like a product form before, so we can easily throw our Monte Carlo at it. But how are we going to break it up? We could try drawing our samples theta from the likelihood for each of these events. Or we could draw samples from the population model and just evaluate the likelihood at all of those points. So it turns out what we do in practice most of the time is neither of those things. We draw samples from a fiducial posterior distribution. And the reason we do this, you've heard about single event inference yesterday, and there's more later in the week. But basically, what this typically gives us is the posterior distribution for the single event parameters given the data and some fiducial population model. And so we can do our same trick of multiplying by 0, essentially, and rearranging with Bayes' rule. And we wind up with this expression here, which you'll see all the time if you look through the literature, that we use samples from the single event posteriors, and we have this same looking quotient here again. We have our new population model, and we're dividing out by the old population model, which is often referred to as reweighting the fiducial event posterior samples. So great, we have Monte Carlo integrals to do our selection function and our single events. We can now write our nice compact population likelihood, and we only have to do n times k function evaluations twice to calculate our likelihood. Fortunately, they're kind of trivially parallelizable. You can whack them onto GPUs and pretend everything's great. And it doesn't run too slowly. But let's track back. We're going to be a bit careful with this. You can then try actually calculating those uncertainties. And so this is the global uncertainty in the log likelihood. And you can see here that this scales like n on the square root of n on k. So what do we want this uncertainty to look like? What's an uncertainty that we can handle in the log likelihood? And basically, it turns out that if you take posterior samples from some analysis you've done, and you look at the likelihood associated with each of those samples, you'll find that as you change the signal-to-noise ratio of your system, you don't really change the spread of log likelihoods in the system. And so what you need to be constant is basically this uncertainty in the log likelihood. And this means you need the number of samples per event to scale like the number of events you're looking at, which means that as your population grows in size, your computational cost rises by a factor of n squared. And this n squared means after O2 we had 10 events, and then after O3 we had more like 90, and so the calculations we're doing are now close to a factor of 100 more expensive than they were at the end of O2, and if we ask what they're going to be like at the end of O4, I don't want to go there. But so this is just a numerical demonstration that Jacob, who's in today, did for a paper we wrote recently, showing that you do get exactly this square root k decay in the uncertainty here as you increase the number of population samples. And so, okay, so that's where we are. And now I'm going to move on to some of the potential ways we can do things a bit differently to hopefully avoid some of these problems of having 400 events and it taking until O5 to analyze the O4 data. So what we really want to do is try to get rid of using these fiducial samples and potentially just getting rid of these Monte Carlo integrals entirely. So to do that, we need some way of modeling the underlying function. The reason we use these samples from the fiducial posterior distribution is because it's expensive to calculate that likelihood of data given signal parameters. It involves calculating a waveform and then comparing it with the actual strain data. And so that's expensive if you're doing that for hundreds of events. And other reasons you might want to get rid of this is that it turns out Monte Carlo integrals work really well. I'm going to jump back a lot. If you have these two functions, f and g, if the support of f is much larger than the support of g, then your samples from g will be concentrated in a very small region in f, which will have essentially a constant value, and so you do a great job. But if you try to do it the other way around, and you instead drew samples from a very broad distribution, and then you were trying to evaluate a very narrow distribution, you can imagine that that's going to be really hard. Because if you're drawing samples from 0 to 1,000, but it only matters if your sample is between 1 and 2, then only 1 in 1,000 of your samples is going to contribute anything. So that's what I mean when you say that, or when I say that having very narrow population models is leads to real pathologies, especially when your population model is a delta function. For example, if you're trying to do cosmology, or if you're trying to model the nuclear equation of state, where you have an exact mapping between the mass of a system and its tidal deformability. And so I've divided how we can try to estimate these underlying functions into basically two categories. Density estimation basically means that you don't need to be able to evaluate your target function. You basically take samples from some distribution and you fit some model to it without ever knowing the functional form of the distribution going in. Or you can do some kind of regression. If your likelihood is very difficult to calculate, you can calculate it at a finite number of points in advance and then try to learn some simple model that estimates it. So density estimation, the methods everyone has heard about, histograms, kernel density estimates. Basically, you take your points, and then with a histogram, you just put your bin heights at how many samples there are in each bin. Kernel density estimate, you have a little Gaussian on top of each of your samples. And so these also scale quite poorly as you increase the number of dimensions. For a histogram, if you try to go to n dimensions, you again have this exponential scaling with the number of bins you need for your space. And then these, continuing on, the kernel density estimate and the Gaussian mixture model are kind of similar in spirit. They attempt to fit a smooth distribution which is composed of a bunch of Gaussians, which means that it has difficulty with hard edges. And Gaussian mixture models especially can struggle with some really sharply curved spaces where we have strongly curved surfaces in things like sky location, if you look at these weird bananas we have on the sky. And then there are other deep learning-based estimators, which come with all the usual caveats about deep learning. So they are having some uses, and maybe I'll have time to just give a shout out to some of those later. But to sort of walk through a few of these and say how some people are trying to address the problems with the different methods, you can take your histogram, which is by construction not a smooth function, and then you can try to smooth it in some way. It's something that a couple of different groups have done is to use a Gaussian process to smooth the histogram. Basically, they take the histogram as then an estimate of f of x at the center of each of the bins, and then what this Gaussian process does is it tries to fit a smooth model between all of those bin heights. And so that's one thing that's being done here. This paper that was led by Virginia D'Amelio took a histogram, in this case in 4 dimensions, for this looks like GW 17817, and then from that bin, they trained a Gaussian process based on the bin heights, and then when they generated new samples with their Gaussian process, you can see that they did a pretty good job at recovering the underlying distribution. And so this meant that they had an expression for the likelihood just in terms of these 4 parameters that they could evaluate arbitrarily and draw new samples from quite easily. A kind of complementary approach is something that I've worked on a decent amount, also with Jacob in that paper I mentioned before, where we instead take this Gaussian mixture model and we try to deal with the fact that it only likes smooth things. It doesn't like sharp cutoffs. For example, here you can see that the mass ratio posteriors we often see have very sharp cutoff at the physical limit of equal masses. And there are various other sharp cutoffs we see. And the difference that we introduced is basically to, instead of just trying to fit a Gaussian mixture model in this physical space, you just transform your problem into a space that doesn't have any hard edges and that gets rid of some of the nasty correlations, and then your Gaussian mixture model can quite happily fit this distribution. And this seems quite promising. We've used this for estimating sensitivities, and also, again, this is GW 170817, and you can see again the blue samples, I believe, are the original ones, and the orange are the ones generated from the Gaussian process, not Gaussian process, sorry, Gaussian mixture model in the physical and fitting space, and they agree quite well. They're giving good estimates of it. So what if we instead look for these continuous representations that aren't based on density estimation, but instead you need to feed it some inputs? Again, you can try to get an analytic expression. You can just say the dependence on mass of the selection function looks a bit like m to the 2.2. And so you can try to put that in and hope that that's good enough for your analysis. But it's kind of limited to what you can write down good analytic expressions for. I've already mentioned Gaussian process regression has been tied up with histograms. And these are good. One of the great things about Gaussian processes is they have these well-motivated uncertainties that come with them. So you can actually propagate the uncertainties through as you go. But one of the limitations is that you need to be able to calculate the underlying function at the points where you want to train your process. So one way around that we've just seen is to couple it with a histogram. But other things are, for example, the Rift algorithm that you might hear about sometime calculates very expensive likelihoods for data given given binary parameters, and then it fits a Gaussian process to all of those likelihoods to try to give a continuous representation of the likelihood. And then again, deep learning methods, these are your neural networks. They just learn the function and they do their thing. So again, this is just another example here of a way that people have used, again, histograms and Gaussian process regression to this time do a population level analysis. So this analysis, or analysis based on this, appeared in the GWTC3 companion paper that just came out, where basically now it's a population model. So you populate your bin heights by basically having something like a histogram of the samples for the individual events, and then you impose some smooth condition that if one bin has lots of support, but another one happens to not have any samples in it, you're not going to allow that one to go to 0 because you know it's right next to the one with lots of support, and so you have this smoothing via the Gaussian process. And then neural networks have been used in a few cases. They're very flexible. They work on very high-dimensional data. A neat feature of them is that people really love neural networks. People not in gravitational waves and not in astronomy, but people in businesses that make lots of money really love neural networks. And so there are great bits of software out there for just using neural networks off the shelf that can make it a lower barrier of entry to starting. But as I understand, uncertainty propagation is not standard and difficult to track. And you need to be able to generate your labeled data. Basically, you need to evaluate the underlying function lots and lots of times. So I think the main place that I've seen this used is in evaluating the selection function for gravitational waves, because while we can do these injections and we can do our million injections and then have lots and lots of training data, what you can then do is you can train the output of that with a neural network. So you don't have to do your second million injections to get a better estimate of the global sensitivity. You then just pass it on to your neural network that gives you a really quick answer. And so this has been applied in a bunch of cases and shown to give good performance in evaluating single event or the sensitivity to individual binaries, and also at the population level you can get results that agree with the traditional method using this sensitivity estimate. So after that second digression, we can get back to where we were before, which is trying to think about different ways to evaluate the likelihood. And so I've thrown up this slide again. It does exist twice. And so before, we took an approach which was something like this first one. We didn't quite use samples from the likelihood. We used samples from some fiducial posterior. But instead, we're going to say, we're going to draw samples from our population model. And remember, this is really useful when our population model is very narrow compared to the individual event posteriors. So for example, one of the things that we think we're measuring is that the distribution of spins, or the spins in merging black holes, are very small. And one of the problems we find is that we physically can't measure distributions that narrow with the methods we're currently using. These uncertainties I flashed up before are exploding, and we're actively having to purge those parts from our analyses. So if we can use this method instead, then hopefully we won't have that problem. We can start to probe these really narrow distributions. And similarly, the narrowest distributions being delta functions, you can apply this to the equation of state, which was the main focus of this paper I mentioned a couple of times. And so we demonstrated that by using these Gaussian mixture model fits and these population models that we can draw samples from very efficiently, you, instead of using your fiducial event samples inside your Monte Carlo integrals, you train your density estimate with those fiducial event samples, and then you evaluate that likelihood as much as you want with samples from your population model. This still has the same uncertainty scaling with the number of events, so it's not really a long-term solution, but it does solve this problem for especially this case of estimating the equation of state of nuclear matter. And one of the things we showed in here was that you really have to fit all the things together. You have to fit the mass distribution correctly in order to measure the correct equation of state, and vice versa, which the previous method would not have been capable of doing, really. So, okay, we found this new method that solves this particular problem, but can we not just remove all of these Monte Carlo integrals entirely? And so why don't we do that? So we can remove the Monte Carlo integral for selection effects. I showed those plots before using the neural networks that showed that you can use some kind of regression model to just fit the global selection function. So that gets a tick. Or you could just fit the observed distribution. Currently, a lot of what we do uses these phenomenological models where we say things like, this parameter is the minimum black hole mass, and this parameter is the mass of a typical black hole that's undergone pulsational pair instability supernovae. If you believe that kind of thing, it's great. But the issue is you then can't translate those. You have to fit the astrophysical distribution for those parameters to mean anything, basically. And so if you wanted instead to fit the observed distribution, those parameters, it's harder to say that they're meaningful in any way. And so you would have to really start to drop the phenomenological approach that has been kind of dominant if you were to fit the observed distribution. Which is not to say that's not what we shouldn't do with the correct amount of negatives. Observed distribution may be the way to go in future. So the other thing that we can do to get rid of the Monte Carlo integrals is go back on this thing I did way towards the beginning and just keep all of the single event parameters as free parameters. And now we just have a bigger dimensional space to explore. Generally, it's harder to explore a 300-dimensional space than a 10-dimensional space. But in practice, it turns out to be not quite as bad as it might sound at first. And this is something that is active work by me and others. If you're interested in talking about this later in the week, I'd be very happy to. So just as I start to wrap up, there are some more exotic methods that we can try to throw out. There are these kind of, I mentioned before, the phenomenological modeling that we've done. These are what I see as the other two options we have. The phenomenological modeling sits in a kind of sweet spot between representing the data faithfully and having some kind of physical intuition. So you can basically throw one or the other of those out the window and say, I only care about what the data is telling me, or I only care about what my detailed population synthesis simulations are telling me. And so there are approaches to use both of these things, and I think ultimately, if we had both of these things and we managed to converge on the same inferred distribution with these two radically different methods, then we might start to trust the astrophysical simulations that we're putting all our computing time in. So these are just a couple of papers to flag with this. We've seen this sort of histogram-based method before. This paper in here uses this HDPGMM, which is lots of Gaussian mixtures again. And basically, they've shown that for single parameters at a time, they can fit the distribution pretty well, including incorporating some selection effects as well. So that's kind of promising and is something that samples in this sort of high-dimensional space, but does it with some clever sampling algorithm that knows how to deal with the specific problem. And this other one is a kind of recent paper that takes the output of population synthesis simulations or globular cluster Monte Carlo codes and then uses a deep learning density estimator to basically fit that distribution, and then you can compare that directly with the data. And so these have very strong physical assumptions, and so you can, if you trust those models, you can actually tie that directly to an actual, I've changed the way the common envelope works in my simulation, and it's changed the mass in this way, and it makes it fit better. And so I'm going to say that this is the correct model for common envelope evolution. And in the last few minutes, I'm going to get onto some of these goodies, hopefully. So Salvo said at the beginning of the day, hopefully we would understand this plot in the top right by the end, so I'll give it my best go. What this is what we call posterior predictive. So basically, post, we've taken the data, we want to predict what we're going to see next. And so the way we do that is we take our inference about the population level parameters, and we integrate over our uncertainty in those population level parameters to get the probability of seeing some single event parameters given all of the data we've seen. And so this marginalized version is exactly this solid line in the middle that we tend to call the population predictive distribution in our papers for reasons, and then the uncertainty just comes from, instead of doing an integral over this, you just take individual samples from your posterior distribution. And if you do that 1,000 times, you build up some uncertainty. And so this is the inferred population with some uncertainty. And instead of a population predictive, we can say, what's the posterior predictive? The difference between this is the posterior predictive is what we predict we'll observe next, whereas the population predictive is what we expect to merge next. And they're different, obviously, because we have this selection function. And then you can see that these are kind of simply related, just we've got this extra factor of a binary selection term in here. And so these were taken from slightly different papers, but you can see, for example, the mass scaling of the sensitivity means that this peak around 35 solar masses is the global maximum of the observed distribution, while the global maximum of the astrophysical distribution is down at low mass. And the other thing we can do afterwards is we can update the priors that we have. When we look at our single events, we typically just look at them with our fiducial priors that we put in when we do our first round of inference. But what we can do instead is we can do a bunch of fancy maths that is on a bonus slide if you really want to go through the details. But again, we do another Monte Carlo integral over a bunch of terms we've seen before. These are all the kinds of terms we have that we've had before. And you wind up having your posterior, which is updated. And I thought that I added a figure in here. Anyway, you have a posterior that's updated based, I have on the next slide, that was it. You have, in the black is your posterior distribution, assuming your fiducial prior. And then this is taken from the latest populations paper. For two different population models, you then have that your observed catalog depends on your population model, which was always true. We just didn't necessarily appreciate or announce that as strongly as we should have. And so for two different population models in that paper, we can see that they sometimes agree more closely with each other than they do with the fiducial model, and sometimes less closely. So this is basically saying that if you can look at this and you can see two different plausible population models giving different inferred posteriors, that means that we're basically dominated by our modeling choices. And so you shouldn't take too seriously if the fiducial PE for this said that it peaked around a mass ratio of 2, then you shouldn't really take that seriously if it doesn't stand up after you update your population model. And then the very final thing is we have these two different population-informed statements, right? We have our predicted distributions and we have observed distributions. And so we can say, are those two things the same? Because really, if we're predicting something different from what we've seen, then something's gone wrong along the way. So this is what this plot, which I'm not sure if it was in the latest paper, but shows these very strange S's with error bars on them. Basically, in the dark part is this observed distribution, or the cumulative version of this observed distribution that we had on the previous slide. And the light contours are, with uncertainty, the cumulative predictive distribution. And so we want those to, basically, if you see these plots, overlapping is good, not overlapping is bad. So here, these three models are all doing great jobs with the data we had as of GWTC2. And this model was in a bit of trouble because it was starting to show some tension around the edges. So that's basically all I had. This was very quick. If you're interested in learning more of these details, they've been written out by everyone under the sun at this stage. But there's a few here to get going with, especially this Moore and Girosa one went more in the details of this population-informed priors and those kind of things, where they wrote out a nice derivation. That's something that's been particularly confused in the literature up till then. If you want to do your practical adventures, you can grab any of these open source codes. They should be described in the LVC papers, but we try to make the codes and methods we use as transparent as possible, so you can find these and start trying to run your own analyses. Especially, I put this one together recently, this GW population_pipe thing has descriptions on how to download the data you need and run, basically, a bunch of the analyses that were in the GWTC3 companion paper. So that's all. Hopefully, you learned something new and interesting about the way we calculate our likelihoods, and we may go on to calculate them differently in the future, especially as we have catalogs of hundreds to 1,000 events. These Monte Carlo integrals that we spend all our time churning through are not likely to be a sustainable option. Thanks. I hope I was OK for time.